Thank you. Hi, everyone. It's good to see a good crowd and people in the seminar room. I'm sorry that I can't be there in person, but it is my pleasure today to introduce our speaker, Dr. Baoshan Chen. Dr. Chen is a research associate at SoMAS working on carbonate chemistry in the New York Bight. He got his bachelor's and master's degree at Xiamen University, which, as many of you may know, is a very highly respected university in China and internationally, especially in the field of oceanography. He then got his PhD at the University of Georgia in 2015, and then he did a postdoc at the University of Delaware. And then he was a senior visiting scholar at Xiamen University. And so there's a kind of interesting story about that. We started the hiring process for Baoshan almost 3 years ago. I don't want to think about the exact time it took, but in the process, Baoshan had to return to China for his visa in December of 2019, which at the time we thought would be a really nice way for him to visit his family before starting his job in earnest at Stony Brook University. And so then we all know what happened. Baoshan got stuck there for nearly a year, or maybe over a year, but he was respected so much in his field and at his home university that he was able to be a visiting scientist at Xiamen University. So we had to wait anxiously for a year for Baoshan to get his visa, and in February of 2021, he finally arrived at Stony Brook University. And he showed up to what has been called an art installation of water samples that we had been collecting for the last 3 years in the New York Bight. And so he got started right away, and he successfully set up our carbonate chemistry lab. And I'm proud to say, under his leadership, we've almost worked through all 3 years of those samples, and not just worked through them, but generated really high quality data. And so to say he has been instrumental in setting up the lab and producing interesting results would be a really bad pun, but it's true. Baoshan has well over 30 publications, including some papers in Science and Nature Geoscience. He's worked on carbonate chemistry in a variety of systems, including the Arctic, waters off of China. And today he's going to be talking about his work in the Chesapeake Bay. It's been hard, as you know, for Baoshan to meet people. It's not a great time to start a job during a global pandemic, but I would encourage you all to, reach out to him about carbonate chemistry. And he's also learning a little bit of biology in the NI lab and working on our New York Bight project. He's also has experience training students on instruments and, working on carbonate chemistry. So I hope you'll get to know him after this seminar and during the pizza, which I'm going to be missing after his talk. We are recording, and I will ask that people that are online maybe put some questions in the chat, and I'll try to just call on people online. We also have people in the audience, and so Baoshan, I'll have to rely on you to call those people and repeat the question for those questions. But with that, I'll take it away, Baoshan.
Thank you, Jeanette. So a little bit nervous to give the first presentation here. So first, I would like to thank Jeanette for inviting me, and Josie is not here, so I would like to thank Josie for organizing. So, and thank you all for coming. So it's a really honor and pleasure to give you this presentation here. So this is the topic of interest to me about acidification and buffering mechanisms. So I hope this talk will be appropriate for OSC. So today I'm going to talk a little bit about how inorganic carbon cycling buffers Chesapeake Bay acidification summer. So I also would like to thank my collaborators. They are Vichy Kai's group at the University of Delaware, Jeremy Tester's group and Yumi's group at the University of Maryland. And this research was supported by NOAA. So today I'm going to talk about the hypothesis with limited support from field observations, but it was published in 2020. So this is a line of the common topics I'm going to go over today. So include the background, the hypoxia, anoxia, and air water CO2 flux in the Chesapeake Bay, and the eutrophication due to acidification in summer, and spatially decoupled calcium carbonate cycling, so buffer acidification. So before I give my talk, I would like to briefly go over some basic parameters for the organic CO2 system. So
Baoshan?
students.
Baoshan, I'm sorry to interrupt. It's a little hard to hear you. Can you either speak into the microphone or maybe move the microphone closer to your mouth?
Can you hear me now? Okay, hear clearly. So I just raised the microphone a little bit.
I think that's a little better.
A little better. How about now?
Can you maybe keep talking?
So can you hear me clearly now?
Yeah, I think if you talk directly into it, that would be the safest. Sorry.
Yeah. So if the people on the back hear me, okay, great. Yeah. So in case some students are not familiar with it, so basically there are 4 parameters in the CO2 system. So including the dissolved inorganic carbon, total alkalinity, partial pressure of carbon dioxide, and pH. So technically, we can use either 2 of the 4 to calculate the other 2, but with uncertainties in the calculation, particularly in the brackish water and extreme environments. So some solution of work is to be done to get it improved. So so these 4 parameters are widely used in studying carbon cycling, either in the sediments, in the water column, and in the air-water gas interface. So overall, so carbon cycle, so including the inorganic and organic. So sustain the functioning of the marine ecosystem. So and I think it will be a key component in understanding how ocean responds to the future climate change. So although we have spent substantial time to just work on it, so there remain a paucity of knowledge in the carbon system. So including such as how carbon system responds to the future climate change. So how carbon system coupled with the other biogeochemical cycles. There are still a lot of uncertainties in the carbon budget estimation. So also we still don't know a lot of controlling mechanisms of carbon cycling in various environments. So I hope carbon cycling can just inspire the research interest of the Colloquium perspectives, graduate students, and so on. So as we know, so fossil fuel burning and human activities raise the CO2 level in the atmosphere. So the uptake of CO2 from the atmosphere increase the surface water CO2 while decreasing the pH in surface water. That's what we call ocean acidification. So far, the surface ocean pH has been decreased by 0.1 units since the Industrial Revolution, and is projected to decrease 0.4 units by 2100. That's the end of this century. So 0.4 units is a very large number in pH decrease, since a drop of 0.3 pH units corresponding to a doubling of the hydrogen ion concentration. So we know some organisms may thrive in a more acidic environments, but most of the organisms are not doing well in this kind of environment, particularly for calcifying organisms and some of the non-calcifying organisms. So the ocean acidification in coastal ecosystems is more complex than the open ocean. So due to the compact sources and transformations of carbon and human activation. So usually the hypoxia and oceanification tends to occur in the water in the coastal ocean. So that's caused by the decoupling of the surface production and organic matter respiration in water, such as in water. So the respiration of organic matter consumes oxygen, release CO2, and decrease the pH. So that's what we call the eutrophication, induced oceanification in coastal waters. So in recent years, the hypoxic sites around the world are increasing. So especially in the marine organisms and some just ecosystems. So on the other hand, so we also say the synergistic effect. That is, the ocean acidification can be enhanced by eutrophication induced hypoxia. So this is like this. It will lead to a greater pH increase in hypoxic water. So you will see here. So if we are in oxygenated water, the decrease in pH is smaller than hypoxic water. That's because the reduced buffer capacity for the carbonate system. So and the co-occurrence of the low DO and low pH in bottom water has been reported in many coastal ecosystems, such as in the Gulf of Mexico, as well as in the Long Island Sound and many bays and estuaries around our island. So the Chesapeake Bay is a very ideal site to study the eutrophication and oceanification, since it's seasonally stratified and there's a seasonal hypoxia and anoxia there. So as the largest estuary in the United States, the Chesapeake Bay is characterized by the low water residence time, which is also about 6 months. And it has a deep and narrow channel, which is seasonally stratified. But in the past several decades, people have conducted a lot of research about the nutrient organic carbon and sediments. But the inorganic carbon cycle has never been systematically studied and reported in the Chesapeake Bay. So it usually it's studying anoxia and hypoxia. So the Chesapeake Bay was just divided into 3 major parts, including upper bay here, the middle bay, and the lower bay. So due to the stratification in summer and limited water exchange, since if we take a look at the topography, it's deeper in the center and shallower at the head of the bay and mouth of the bay. So the Chesapeake Bay is experiencing the hypoxia and anoxia summer. So the hypoxia and anoxia is related to the nutrient load. So with the onset of hypoxia and anoxia in May and break up in September. So although in recent years, we have reduced the natural load amount, the hypoxia and anoxia still exist there, only with a shrinking volume. That's what you can see. There's a difference between 1985 and 1999 and 2015. So we also would like to know, in the Chesapeake Bay, so we know that eutrophication induced oceanification. We would also like to know if the organic CO2 would affect the acidification in the Chesapeake Bay. So as we know, estuary only just occupy a very small area, just 0.3% area of the surface water area, but it releases a lot of CO2 in air. With most of rivers releasing CO2, only some rivers or estuaries are taking out CO2. So people always think that since the estuary is oversaturated in PCO2, so the increasing atmospheric PCO2 will not affect the oceanification or contribute to oceanification in estuaries. But the other people argue that they suppose with the increasing atmospheric PCO2 level, so the estuary's ability to degas CO2 is just limited, just more of the CO2 can be trapped still water. So we still can call it acidification caused by anthropogenic CO2 emission, but the amount is very tiny. But in the previous research, people with just focus on the small estuaries, so with the shorter residence time. That's why high CO2 water can just be quickly just flush into the coastal ocean, with all of the river saturated with PCO2. And we people also just focus on the larger rivers such as the Mississippi River and Chanjiang and a lot of Amazon River. But very few studies have been conducted in the large bays with moderate water input and long water residence time, such as in the Chesapeake Bay and the St. Lawrence Estuary River in Canada. So we have no idea what will happen in the Chesapeake Bay. So to understand, so if anthropogenic CO2 will affect the acidification in the Chesapeake Bay, we conducted the bay-wide monitoring of surface PCO2. So over 11 months a year. So this is the figure of the surface PCO2 from February to December 2016. So we have divided the Chesapeake Bay into 3 regions, upper, mid, and lower bay. So overall, the upper bay is releasing CO2. So we can see that atmospheric CO2 is around 400 microatmosphere, that's in green. So the warmer color indicates the estuary is releasing CO2, and the cold color is taking on CO2. So the upper bay is almost a CO2 source, and the mid bay is a transition zone, just switching from a CO2 sink to a CO2 source, or vice versa. The lower bay is almost equilibrated with the atmosphere CO2. It's close to 400. So if we take a close look, so this figure, so what caused this kind of distribution patterns? So the quick decrease in PCO2 in the upper bay is caused by the long residence time. So in the Chesapeake Bay. So since the CO2 system is a boundary system, it takes a lot of time to get the water to be equilibrated with the air. Usually it takes about 2 to 3 months. But since the Chesapeake Bay has a very long water residence time, so when the water leaves the river mouth and reaches the lower end of the upper bay, most of the CO2 can be gassed to the atmosphere. So that's why when the water flushes into the middle bay and lower bay, so what is clear, the surface water PCO is low with a nutrient input. So the biological production utilizes the DIC to decrease the PCO2. So in the lower bay, with the less input of nutrient, so this bay shows a very consistent PCO2 distribution. So although you will see the monthly variation, but the annual average is very tiny. So we could say in the Chesapeake Bay, so acidification in the mid and lower bay can be affected by both eutrophication and uptake of anthropogenic CO2. But the latter might play a minor role since the small CO2 ARC gas flux. So to study how large estuaries such as Chesapeake Bay just to respond to eutrophication and acidification. So we conducted bay-wide research, particularly in summer. So when the acidification and anoxia, hypoxia were well developed. So that's why in 2016, in August of 2016, so we sampled the mainstay of the Chesapeake Bay. So DIC, TA, pH, and DO. So these basic parameters were connected. So in order to just more precisely and accurately estimate the saturation state of calcium carbonate, so we analyzed the calcium concentration separately. So that's because in coastal water, so calcium carbonate solution estimation so might be important. So if we just use the DIC parameters to make a calculation, so we might just miss some important signals. So here, the saturation state of calcium carbonate is referred to as omega, so which is presented here. So it's calculated by the product of calcium ion and carbon ion concentration, and then divided by the solubility product. So when omega is smaller than 1, it means this water is corrosive. So it will cause the calcium carbonate to dissolve. And when omega just larger than 1, that means calcium carbonate formation. So there are two major polymorph forms for calcium carbonate. There's calcite and manganite. So since the latter is more soluble, so people usually just calculate the omega, just a manganite, just to indicate the quality and acidity, and if it's detrimental to the organisms. So based on this research, it's very clear. So in the summertime, the certification developed in the top 10 meters. So in the just block ALC gas exchange and the replenish of the oxygen water from the atmosphere to the bottom water. So the respiration of organic matter just creates the hypoxia. Then as the concentration is controlled by 63 micromole per kg, and anoxia, zero oxygen. So with no oxygen, so the sulfate reduction just produce hydrogen sulfide, but its concentration is low. So correspondingly, the releasing of CO2 just resulting in a low pH and very high PCO2 concentration as here, as well as very low just omega saturation. This number is below 1.0, 1.5. So we also noticed just in a nearshore station, the station CV2.1, CV2.2, that's here. So we precisely analyze the calcium concentration. So we found some concentration of calcium, the ACTA, and omega very low here. So in addition, so what we would like to know is about the controlling mechanisms. So we take a look at the relationship of the DIC and the TA and the salinity. Here, this figure looks complex, but we can just decompose it. We have several examples. The first example is the Susquehanna River, so which contributes to 60% of the fresh water into the Chesapeake Bay. So the second example is offshore example. So with these two examples, we can see the mixing between the river water and offshore water. The third example is CB2.2, as here. So it shows the smallest DIC and TA. So and the last example is here, station L1. Station L1 is right outside of Baoshan Bay. So it might just represent the best mixing scenario, since the offshore water might be just altered by the other biogeochemical cycles. So we have noticed that here is the most important thing. So usually just the estuary, the TA is semi-conservative, and it's just slightly influenced by the photosynthesis. Here we can see a very big decrease in DIC and TA. We can call it the removal of DIC and TA. As well, if we take a look at calcium, and calcium concentration versus salinity. So usually in mixing, calcium is almost conservative. And you can see in the high salinity region, so it's almost conservative. But at the salinity range, from 0 to 15, we can see some removal of calcium. So all from this figure is very tiny, since the concentration of calcium is very high. So if we would like to see the difference, we can calculate the delta DICTA of calcium. So that's what we follow the mixed line of these two examples, and then to predict what the DIC and TA concentration should be on this line. And we just calculate the difference between the measured number and predict the number to see the removal of DIC, TA, and calcium. That's what you see here. So that's the green dot is calcium. the blue is TA and the red cross is DIC. So from this figure, we can see the first is a lot of decrease and removal of these few parameters. So if we take a look at the change of the acid TA, so you might have noticed the difference and change of the acid TA, the ratio is close to 1. So if we take a look at the photosynthesis, the ratio of the acid TA change is about -6. So it means the decrease in DIC will result in an increase in TA instead of decreased TA. So, and we can take a look at the removal of calcium ion. It's about 400, and the DIC TA removal is about 700. So as we know, for calcium carbonate formation, just 1 unit change by a calcium concentration, such as decreased by 1, the DIC will decrease by 1, and the TA will decrease by 2. So if we take a look at just the largest deficit of these numbers, the calcium change is about 93, is about 400. TA change is 700. So this ratio is close to 1 to 2. So it means, so the removal of a calcium concentration can be used to build the calcium carbonate minerals. So, and if we take a look at the DIC, so since 1 decrease in calcium just decrease DIC by 1, but here the DIC decrease is almost the same as TA. So it means there's another biogeochemical process removing DIC. So usually DIC can be consumed by photosynthesis. So it can use DIC. But as we have shown, that in the upper bay is the source of CO2. The PCO2 is oversaturated, and the DO is undersaturated. So the overall is respiring organic matter instead of producing organic matter. So the DIC can only be removed by degassing. So our another calculation does support this assumption. Most of the DIC decrease can be explained by the degassing. So it tells us one story, that is calcium carbonate production. The demand is very huge, and it's very important to compensate in the upper bay. So we would like to know what are the sources of calcium carbonate in coastal waters. So calcium carbonate can be formed just a biotic precipitation or biotic that is controlled by photosynthesis. So and the calcium carbonate formation has been reported by a lot of processes and related to many species such as coral reefs, calcareous algae, bacteria, workers, fish, seagrass. So in the Chesapeake Bay, we have no this kind of data. So we have no idea about the biomass of these species. We have no idea of the calcification rate. So what will be the control mechanism? So but we have noticed most of the DIC and TA and calcium concentration was removed in a very small area. That's the area just between the river mouth of Susquehanna River and the CV2.1. So it gives us a hint. So to support a larger amount of calcium concentration removal, so we should have either high density, just a high biomass of species, or a very high calcification rate. So given the biomass of algae and bacteria, and given the mobility of fish and milkers, so I think this for just species might not contribute a lot just to the calcium concentration removal. And I have no idea what that's coral reef. I don't think that's coral reefs in the Chesapeake Bay. So we have hypothesis. That's the seagrass contribute to the calcium carbonate production in the upper bay. So for the calcium carbonate production mechanisms for the seagrass, so it's biological, it's like an enhanced process. So the calcium carbonate crystals can be produced within the cell walls or just as external deposits just on the blade of the leaf. So that's caused when with photosynthesis can just increase the pH. So the surrounding water has a very high pH. The diffusion layer just close to the leaf, so I could have a higher pH. So in an ideal situation, which favors the precipitation of the calcium carbonate from outside the leaf. So yeah, so and we also know, so in this area, just between the speed 2.1 and the Susquehanna River, there's a Susquehanna flat, and there's a lot of, we call it submerged aquatic vegetation, we call it SAV bed. There's kind of sequence. So, and from sense data, which is located inside the SAV bed. So we have a long-term monitoring pH and dissolved oxygen. So this green shaded area corresponds to cruise duration from 2016. So and we have noticed that the dissolved oxygen concentration and pH are very high. So dissolved oxygen can be up to 180%, and the pH can be up to 10.1. That's extremely high. So it will support our hypothesis that in a high pH environment, so the seagrass might be able to just precipitate calcium carbonate either within the cell or just outside, just on the leaf. So if we just take a look at the other species in Chesapeake Bay, so in Chesapeake Bay, there are a lot of SAV beds along the bay. So they have different community types, including the freshwater low salinity type, the medium salinity type, and the high salinity type. So in the 1950s, so most of the SAV bed declined due to eutrophication. So but people tried their best to do the recovery. So from the 1985 to 2015, the nitrogen concentration has increased by 23%, and the SAV cover has increased by 300%. So and they have a restoration target, but you might have seen. So the best recovery of the SAV bed can be found in the tidal fresh water and Halian. That's a salinity range between 0.5 to 5. That's around the keys around this area. But for the Halian salinity, it's 5 to 18, so it's almost unchanging. And at the high salinity, the SAV bed increase and then decrease. So it means in our study area, we are going to have dense SAV bed. So yeah, another research has shown, so the greatest recovery of the SAV bed is in the Susquehanna flats. So starting from 2005, so you can see the density of the SAV cover increased and to be stable up to 2010. So it supports, on the other hand, of our hypothesis that calcium carbonate may be produced by the SAV bed. So if the SAV bed can contribute to the production of calcium carbonate, so how the calcium carbonate produced and contribute to the cycling in the Chesapeake Bay, and how could it buffer ocean acidification? To answer this question, we made another hypothesis that can conduct some work. So since we didn't just access SAV bed in 2016, so we tried our best to take some samples in 2018, in June and in September. So in June, we found the SAV bed was sparse, but in September, the SAV bed was dense. So I will take a look at pictures. And these are some pictures I took in 2018 September. So you can see the boundary of the SAV bed and then adjacent of the water. So if you just go inside, you can see the very dense seagrass. So if we go back to take a look at the data we collected, so for each cruise, we have two transects, a western transect and eastern transect. So the SAV bed is located just on the eastern transect. So we have some parameters. The first is pH, that's the black triangle, and DICTA and calcium. So you might have noticed that. So once we go into the SAV bed, pH increased very quickly. So from 8 to maybe 9.6. So and in September, so it can be up to 10.1. It's very high. So the only difference is the DICTA and calcium between these two seasons. So if you take a look at calcium as green dots and the TA, so in June, so you can see the DIC decreased a lot, but the concentration of these two parameters stayed almost constant. So it's supposed photosynthesis usage of the DIC. So and there was tiny or no production of calcium carbonate. So if you go into the September cruise, you will see what we observed in our 2016 cruise. So you can see a bigger removal of calcium carbonate as well as the TA and the DIC. So if we make a comparison, so let's take a look at the other calcium, the other TA, 2018 as a bad. So it's about 300 and 400. So if we make a comparison with that in 2016 at the station CB2.1 here, so they are very close. So it means so the calcium production in SoMAS bed might support what we observed downstream. But why does at CB2.1 in this season you didn't see just a significant decrease in calcium? So it might be related to flushing. So it gives us another hint is that so the water just in SoMAS bed has been removed calcium. So the calcium concentration in the DIC decreased, and this water can be flushed down to CB2.1, so there's a type A. So that's why in the same cruise we didn't observe the calcium removal, but in the other cruise we observed the high calcium removal. It's just the water, well, previously just located here, here. So we also took some just samples, and we also took the same samples. So these two are the major species. So I don't know how to pronounce that. So but we just to just locate the calcium carbonate use the skin electron microscope. So in this species, so we can locate the calcium carbonate clusters. The size, the cluster size is about 2 micrometer. So once we locate the calcium carbonate, we just to test the atomic composition. So you will see this is the calcium carbonate aggregate on the leaf. Now this is the pure calcium carbonate crystals. So their atomic composition are almost the same. So it means calcium carbonate produced on the leaf is almost the same as the unpure calcium carbonate. And there's no other chemicals inside. We also just wait, just to wait the dried leaf and just measure the calcium carbonate using the gas chromatograph. So in June, we know so there was no calcium removal, so you cannot detect a larger amount of calcium carbonate either just in the leaf or in the silicon samples. But in September, so you will see a lot of calcium carbonate. It's about 6% weight by weight in the leaf. But in the sediments, it's just 0.2. The difference is just 25%. So we might hypothesize that just before the SoMAS bed died, so most of the calcium carbonate just stays on the leaf. So it might also just support a hypothesis is calcium carbonate can be flushed down to the lower bay and the middle bay instead of to be buried into the sediment. Otherwise, we can detect calcium carbonate in the sediment in the next year, unless it's dissolved during the winter. So if we just take a look at this one, so it's not very obvious. If we take a look at this image, you will see the increase in DIC as well as the calcium carbonate concentration and total activity, but it's not obvious. But we should ask, so the increase in calcium and total activity, so what's the source? where is the source from? Is it a local source in the North Bay and Mid Bay, or from a network transport from upstream to downstream? So in this case, we have no other evidence, so we use a sediment module. So incorporated into the rocks model. So we tested 3 sizes of particles. That's 2 micrometer, 8 micrometer, 20 micrometer. So this figure shows the result from 2 micrometer. So the model shows the very fine particle. So once it's released from the upper bay, just the mouth of the Susquehanna River, so it can reach the middle bay within 10 days. And in the next month, so it can affect the lower bay. But for 8 micrometer, or it can reach the middle bay within 10 days, but it will not affect the middle bay a lot. So for the larger size, it only can be checked in the upper bay. So with these, and we know the calcium carbonate construct has a size of about 2 micrometer. So we assume the particles can be flushed down, although we don't know if it's true. So based on this simulation, so we apply another mixing just scenario. That's mixing using the lowest DIC-TA and calcium concentration. That's at station 2.2. And with the L1, that's a station generated just outside the Chesapeake Bay. So the reason is that, since the Chesapeake Bay has a very long water resistance time, so the chemical properties cannot be restored to the original concentration very quickly. As well, since the calcium carbonate has been removed out of the system, it's also impossible just to raise the concentration back to this number and mixing this offshore water. So it means the element has been changed. We do the analysis of conservative mixing. So we apply this mixing for DIC and TA and calcium, and to calculate the DIC and TA. So you will see there was increase of calcium ion concentration as well as DIC and TA. So the largest increase is at a salinity range of 15 and 20, and then decrease. So 15 and 20 is, corresponds to the area in the middle bay and in the boundary of upper bay and middle bay. So it means if the particles has been transported from upper bay to the lower bay, it can be dissolved and mediate acidification. So we also decomposed the change in DIC and TA into several processes. So including the aerobic respiration, sulfur reduction, carbonate dissolution, and other processes we don't know that might be related to the sediment water exchange and water gas exchange. So the method is we calculated the pH. pH is calculated from the pH measured minus the pH, so excluding the process we would like to analyze. So give an example. If we remove the contribution of calcium carbonate dissolution, so it will just decrease pH. So the delta pH will be a positive number. So a positive number means this process increased the water pH. Negative number means this process decreased the pH. So it's easy to understand. The respiration release CO2 and decrease pH. So its net effect is negative. And the solution of calcium carbonate increase TA and use CO2. So it will increase the pH. So from this number, you will see with the calcium carbonate solution, the pH increase can almost just counterbalance the respiration cause the pH decrease. But overall, the other processes still decrease pH. So 0.6 is a very large pH unit. So if there were no calcium carbonate solution in the subsurface water of the mid bay, the pH would decrease by up to 0.6 units. 0.6 is very large. We know as surface ocean has been decreased by just 0.1 in the past marginal years, and another 0.3 by the end of this century. but the dissolution of calcium carbonate will contribute to 26 units. So, so that's why we think although we have many unknowns, but this process must be very important. So, with this research and hypothesis, so we have a conceptual model for self-regulating pH boundary mechanisms. So the Chesapeake Bay is estuary that might be different from other lagoon and coral reefs. So that means the difference is the calcium carbonate produced can be flushed to downstream instead sinking down into the sediments in the same location. So since we have no data about biomass and we just can assume, so both the SAV bed in the Susquehanna River threat as well as the other just inshore SAV beds all contribute to the production of calcium carbonate. So this calcium carbonate particles can be transported once just due to tidal influence, strong wind, flushing in the water. So these particles can be transported into the mid and lower bay. So in mid and lower bay, since due to stratification, so the pH is low, it's acidic. So the subsequent dissolution of calcium carbonate will increase pH and alleviate acidification. So we have a take-home message is that the Susquehanna River flats and other SAV beds, so on the flank of the bay, could produce calcium carbonate particles. Calcium carbonate particles can be transported to the mid and lower bay to buffer the subsurface water acidification, so by increasing pH by 46 units. So another important indicator is that once we reduce the nutrient inputs in the Chesapeake Bay, so it will not only reduce the eutrophication and hypoxia, so it will also increase the density and area of the SAV bed. So it will further just produce more calcium carbonate, which can be transported downstream and buffer oceanification there. So it will this process just have a positive feedback to alleviate acidification. On the other hand, this one need our research is very limited. We never sample the PIC, that's the calcium carbonate. We don't have other biological information, just about the sources of the calcium carbonate species. So I think more research is needed to address other sources of calcium carbonate and to address if just downstream transport mechanism to make sure if the particles really can be just transported downstream, or these particles is from other areas. So so at the end, I would like to just occupy you several minutes just to discuss my previous research and my current research. Since I started my work here, so in the middle of the pandemic, so we never had a chance to talk. So as Janet just said, my previous work was to study study carbon cycling in the estuary and coastal oceans in the United States and China. So my master research was to study the CO2 system in the South China Sea, as well as the upward area. So this is a feature area. I'm very interested in the interaction of the river pool and the upward water. So it might increase or decrease activity. So my PhD work was to study the CO2 dynamics in the Arctic Ocean. And after that, my postdoc work to study oceanification in the Gulf of Mexico, as well as the US East Coast and the Chesapeake Bay. So I should say my previous research in the Arctic was amazing. So yeah, that's what we took one samples in the Arctic, and then we saw polar bears. So we have really good findings and I can publish. So my current research at Stony Brook is to study oceanification and carbon cycling in the New York Bight. So I have to prepare an oceanicator just to see how health of ecosystem is. So so in the past 1 year, so we have set up a carbon chemistry lab. So with the DSC and TA system, with the PCO2 system installed on seawall, on seawall, and high precision normals like pH analyzer that I developed. So with these instruments, we are able to analyze carbonate chemistry, just not only for coastal water, but as well as the ocean water with a very high precision and accuracy. So we, in the past 3 years, we conducted a lot of research courses to study the carbon cycling and its controlling mechanisms in the New York Bight. So all of you the pandemic and bad weather, well, we don't have fully coverage for imaging cruises, but that's good enough just to give us a snap understanding of what happened there. So so my research interest right now, and this is related to my current work, is about the cold pool in the New York Bight. So in the mid-Atlantic Bight, there's a cold pool, so on the shelf. So I would like to see what will happen in the future in a moisture ocean. So since we know there are a lot of stresses, including the ocean warming, heat wave, input of the moving organic matter, so that the development of acidification, hypoxia, anoxia. So and we have no idea since high latitude water just does is more sensitive to oceanification. So for several reasons. The first reason is the buffering capacity, and for high latitude water is low, so it can be affected by acid exchange very quickly. Another thing is it has low temperature. It can dissolve more CO2 into the water. So that's why the Arctic Ocean is the most sensitive area. So we have just published a lot of paper about oceanification in the Arctic Ocean. So I'm very interested in what the future of the New York Bight will be. So that's what I would like to do. So we have our previous result just reported the ocean sensitivity recently about the controlling mechanisms and LC flux in the New York Bight. So and we are developing ocean indicators such as the surface omega saturation state, there's a seasonal variation, the surface pH, as well as the subsurface omega saturation, subsurface pH. So I hope so, and I'm looking forward to potential comparison in the future. So that's all of my talk. Thank you very much.
Okay. We have one question in the chat. Chris, do you want to ask your question? I think you can turn off your mic.
Sure. Yeah, just wondering, firstly, great talk, very, very impressive. So congratulations on great talk, multiple very impressive data sets, obviously from all over the world. So congratulations on all that. And that really great monitoring the Chesapeake. The one thing I'm wondering about is the, when you look at that area where the seagrass is recovered, the Susquehanna Flats, I believe it's called. It's very, very shallow, and even that area is very small. So, that's just a tiny fraction of the, it has to be small because it supports SAV. And of course, the Chesapeake is one of the biggest estuaries in the nation. And so I guess I'm wondering, given the very shallow and small nature of that region, what fraction of the total calcium carbonate and or alkalinity that's getting delivered to that very large estuary is from that region versus other sources upstream of it or along the main stem of the estuary?
This is a very good question. So, so you're right. That area is very shallow and a small area. So we tried our best to calculate the contribution of calcium carbonate from the Susquehanna Flats just right before the ocean census meeting. But we found it's very difficult to make an estimate since the calcium just the percent weight of the calcium carbonate in the leaf and the sediment is very low, just 5% and 0.2%. So it means we need a lot of just seagrass just to contribute a lot of calcium carbonate just buffer the acidification in the mid bay and the lower bay. So we tried to get the volume of and the weight of the SAV bed, but currently we still don't have the data. But just in my mind, so I agree with your comment that the contribution for the SAV bed might be minor. I suppose there's another source or other sources from the flank of the bay, so or even from the other rivers. So since if we take a look at the volume of the mid and the lower bay, so the volume is very large. So if we times the volume with the concentration decrease of calcium and TA, so it means we need to have a lot of calcium carbonate to compensate this increase in pH. So I should say I cannot answer your question right now, but I'm very interested in your question. Thank you very much.
Thank you.
Baoshan, I don't see anybody hands up here on the Zoom. So if there's some in the room.
So, very nice talk. What portion of the total discharge from the Chesapeake comes from the Susquehanna?
60%.
60?
Yes, 60.
And that discharge does flow over the bed, right?
Correct.
Yeah, so 60% is across the bed.
Sean, maybe you said it and I just missed it, but so you talked about the different species by salinity range.
Yeah.
Oh, what do you have any? Can you comment on the calcium carbonate production by the various species in those? Do you have any sense of it?
Yeah. So I have no sense since if we just look at the other paper, so when they report the calcium carbonate on the leaves, so they report the different species. So in the Chesapeake Bay, we have our dominant species. So at least 7 or 8, if I'm correct. So we identified 2 in the Susquehanna bed. So, but we just identified the calcium carbonate in one species, with the other species just with very tiny amount of calcium carbonate. So,
But we don't know anything about the mid salinity.
yeah, we don't know. So once we finish this project, we tried our best to collect more samples, but we failed. So since we are not biologists, we have no idea where to take these kind of samples.
Collaboration.
Yeah.
Other questions?
Yeah, I think it's a great lecture. Great seminar. It's very related to the core course, the oceanography course. So it's great for our students to get to the real world, but from the art with from the oceanography. It's great. And I just noticed that there's a part talking about the PCO2 in the Bay Area. It's that the upper Bay Area mentioned that the retention time is longer, so the decrease in the PCO2 was from very high point to a lower stage. In that area is caused by the degassing process.
Yes.
Is there any data or stuff that is normalized by the time?
Yeah, you can make this kind of calculation. So overall, so the average, so the vertically integrated average of the water resistance time in the Chesapeake Bay is 6 months. So, but if we take a look at the surface mid depths and bottom depths, they are different. So, but if the water just flows from the upper bay to the mid bay, it usually takes us about 2 months. So we can do this kind of calculation to see how long the CO2 can be degassed to the atmosphere completely. So it's very easy if you just use the acid and PCO2. So you can calculate the LC gas flux at a very small and very tiny interval. So and this change will affect the acid concentration in the place downstream, and you can calculate the PCO2 and calculate the analysis of flux and do the same. So the final calculation you will see might be about 1 to 2 months for about the PCO2 number of 2,000 microatmosphere to be down to about 400. Yeah, that's why. So in the upper bay to the mid bay, you can see a quick decrease of PCO2. Yeah, that is the reason.
Yeah, what are sort of the major contributing sources of eutrophication, and how would you mitigate those in such a densely population?
And that's the nutrient load. So in the Chesapeake Bay, the nitrogen input from the farm land use is very large. So in the 1950s, since the population increased and the fertilizer use a lot in the Chesapeake Bay, so we noticed that just the acidic bed declined a lot, almost extinguished. So that's why they have just set up a Chesapeake Bay program with a long-term monitoring. So that's one of the best monitoring program worldwide. So it has about 50, 60, 70 years monitoring data. So with a lot of efforts, so people have reduced the nutrient load, and we have seen the recovery of acidic beds.
Any questions? No, in the chat. In that case, thank our speaker one more time. Thank you, guys.